So we talked a little bit about the difference between the kinetic energy of rolling and the kinetic energy of sliding. And to make this a little bit more clear, I'm going to have a little incline here with a box that's just sliding down, right? And let's say the box has a mass of 5 kilograms and that it's sliding at a speed of 10 meters per second at this moment. Okay? And I'm going to take an almost equivalent situation, same exact incline, where I have a ball, but instead it's rolling down, right? So it's translating and it's rolling at the same time. All right. Same exact scenario. The mass of this ball or sphere, we'll call it a bowling ball, is 5 kilograms, and the velocity is 10 meters per second. And the question is, what is the difference in kinetic energy between these two situations? All right, it's an interesting question. Okay, let's start with the situation of just the block sliding down the inclined plane, right? We know that if you're just sliding, right, you're just translating, then kinetic energy is just 1/2 mv squared, right? So we'll put this in, we'll call this KE1. This is 1, this is 2. Okay, so for KE1, we go ahead and put 1/2 times the mass, which is 5, times the velocity, which is 10 squared. And when I multiply all that, I get 250 joules. 250 joules. Okay, all right. So now let's compare that to this almost identical situation of a ball, but now it's rolling, right? And so we remember that rolling is a mixture of translational movement, right? It's actually moving in this direction. So that's straight up 1/2 mv squared, right? But there's also the kinetic energy of the fact that all the molecules in the ball itself are rotating around in axes, right? And that kinetic energy is equal to 1/2 moment of inertia times omega angular velocity squared. Okay, all right. So we see here slightly different equations, this compared to this. Given that they both have this term, and this, like the kinetic energy of rolling, has this term added to it, it's a hint that the kinetic energy of a rolling bowling ball compared to a sliding block is probably going to be higher. So let's see, let's prove that to ourselves. Okay, first things first, we know that for a sphere, I is equal to 2/5 times the mass of the object times the radius of the object squared. And we also know that omega is equal to the velocity of an object divided by r. Okay, so let's sub that in. We have 1/2 mv squared plus 1/2 2/5 mr squared times omega squared, which is v over r squared. Okay, cool thing about this is this r squared on the bottom here is going to cancel with this r squared, so that's going to go away with that. And then this is just going to become 1/2 mv squared plus 1 times 2 is 2, and then 2 times 5 here is 10, so 2/10 m. The r's cancel out, so I'm just left with the v squared. All right, so now these almost look the same, right, except they have different coefficients. Let's go ahead and find a common denominator of 10. So this becomes 5/10 plus 2/10 for 7/10 over here, mv squared. Okay, look at that. The kinetic energy of rolling is bigger than the 1/2 mv squared. It is 7/10 mv squared, right? And if I sub in these values here, I get 7/10 times mass of 5 times 10 squared equals 350 joules. So just the mere fact that this ball is rolling means that its kinetic energy is 100 joules greater than this block right over here. And so this is just an interesting and fun way to compare situations that seem like they're identical and prove that a rolling object has more kinetic energy than a straight up sliding object.